We have two formulas to develop in this section. Probably the easiest way to develop them is via pictures. Suppose I have two events. I'm going to call them A and I'm going to call it B. This part here that I'm shading in the middle is known as A and B. Now, if I shade the entirety of both regions, so let me come back over here. I'm going to try to copy these two again. Well, not exactly, but now if I'm interested in all of this area, this here is known as A or B. Now I want to disassemble these things into pieces. So what I'm going to do is take this A, and I'm going to take it, part of it, like so. So I'm going to leave out that middle part. So there's A with the missing piece there, and I'm going to do the same for B. So there's B, or what was left of B actually. And then I have that middle piece. So it would be nice if I could break this up into pieces and reassemble it into pieces like this, this, and this. Now, we have things to deal with but this is kind of tough. It's hard to reassemble these things. So what you can do is the following. I'm going to take A again. So here's A with that part that they share, and here's B with that part that they share. If I wanted to get everything that's contained in A and B, if I take all of A and I take all of B, watch, I'm going to shade it differently so that you can see what's going on here. If I want to somehow get a formula that relates these things to these things, look what happens if I take them apart individually. This here and this here, these here, account for more than all of that space because they both count this middle piece twice. See, this one counts the middle piece when you count it. This one counts the middle piece when you count it. And here is the overlap. So how do we get it to work? Well, you can take and put those two together like you did, but then I could subtract off one of the overlaps. So this leads to a formula. The probability of A or B equals the probability of A. So you can see it here is the probability of A plus the probability of B. And I'm going to subtract from that the probability of A and B. Let me put a better star. So that's one for your formula books there. This is the formula for OR. We also have one for AND. And it looks like this. Well, let me start first from the formula that we have. If I do A/B like this, the formula for it is the probability of A and B divided by the probability of B. Now, if I multiply, well, what I'm going to do is this. This is the formula we have. I'm going to put this over 1, and then I'm going to cross multiply. So I have P, A, and B times 1 equals, so now I did 1 times that. Now I'm going to do this times this. So there's one formula. And there's actually two formulas for this. I'm going to write it down. I'll put the stars over here because this is what the formula is. The times 1 doesn't do anything. So I'm going to take it out. You're going to want to write both of these formulas down. I could do P A/B times the probability of B, Or I could put the B first. If you do that, then this one that follows has to be changed to P of A. And so this here is another important formula. So these are the formulas that we have for and or. Now there's some special properties. I don't know if I want to write it. I think I'll mention special circumstances when I get to them. But for now, this is the formulas and what you want to do with them. All right, here's an example. It's here to illustrate what we're going to do. Helen plays basketball for 3 throws. She's a 75% shot. So no matter when she shoots, the chance that she's going to make the next shot is always 75%. I'll use 0.75. The event that Helen makes the second shot is still 0.75 because she has a 75% chance every time. The probability that Helen makes the second free throw given that she made the first is 0.85. Well, that's interesting. Let me have that. This is some information that they have given us here. We'll use that in a minute. That's one of those probabilities with the slash mark. The probability, so let me write that. The probability that Helen makes the second free throw, that was called D, given that she makes the first free throw is C, is 0.85. Very useful. Now then, it's going to ask us that she makes both of them. So this question here, what it's asking us is that both D and C work. So the probability of D and C is what we need. Now the thing that we're given here is this piece. So I'm going to put it here. And you can see that that's the information I have. So when you come up to the formulas, whatever one is after the slash mark is what you have for the P afterwards. So this is times P of C. The idea is to make it almost look like fractions, like you're dividing by C and then multiplying by C as if they cancel out. It's there to help you, I suppose, memorize the formula. Well, anyways, we have this 0.85, and then I have P of C, which is a 0.75. See if I had a calculator around here. .6375. Basically, do just like what I did. Write down the info that you're given and then come up to the formulas and decide which one is the one that you want to use. All right, here's one that we have that's a good, straightforward example to use. Let's start with A. Now I'll reiterate the two things that this is equal to, and you'll want to pick the one that is more useful to you. So one of them was P B slash D times P of D, and that's not the one that they gave me. So I'm going to swap those things in there. So I want D slash B. Since they give me that information, that means this has to be a P of B. Let's put our information in. D slash B is 0.5. And P of B is 0.4. That equals 0.2. And then for the second piece, the probability of B or D, that equals the probability of B plus the probability of D minus the probability of B and D. So the probability of B is 0.4. The probability of D is 0.3. And now from the first part we figured out this part is 0.2, and we end up with 0.5. Next example, a lot of the problems here you can do just by thinking them out, but nonetheless, I want to use some formulas to illustrate them. So what we're trying to find is the probability that he plays, a senior picked at random will play college or play sports. And they tell you all about their seniors. Out of the 200 seniors, 140 of them are going to college next year. 40 are going to work. And then you've got the rest are taking a gap year. So that's 20 students taking a gap year. And then they give you information about students who are playing sports as well. So we've got 50 are going to college and they're going to play sports. 30 seniors are playing sports, but they're going to go work. And then finally, 5 of the seniors taking a gap year play sports. So the question is asking us, what's the probability that they are going to college and play sports? So I'm going to use C for college, S for sports. So it's going to equal P C/S times P of S, or P of S/C times P of C. So here we just want to find out which ones we have. I got P of S and P of C. Let me see, where is this? We have 140 will be going to college. So 140 out of 200, that's the probability of going to college. So I'm going to write it as a decimal, 0.7. Then the probability that they're going to play sports in and of itself, 50 of the seniors are going to play sports. 50 of the college-bound seniors are going to play sports. 30 of the seniors play sports that are going to work. And then finally got 5 here. So I have 50 plus 30 plus 5. There's a total of 85 out of 200 playing sports. That's 0.425. So what information do I have here? Well, I'm going to try this one here, this first one, and see if I'm successful. All right, so assuming that they're going to play sports, so there's only 85 of those students. How many of them plan on going to college? Of the 85 students, we know that 50 of those are going to play sports. Now, this is the really coolest thing about this. The probability that they're going to play sports, if I write it in this format, in fraction format, look what happens. The 85s cancel, and you get 50 over 200, which is equal to 0.25, should you want the decimal for it. Now, there's a second thing I want to say about this as well. You could have done this without all this rigmarole. I just did that to illustrate the formulas. Instead, we knew that CNS, the number of people that were seniors and, planning on going to college and play sports, we were already told there's 50 of them. So basically, it's just reading comprehension you could have used to get this answer, but I wanted to exploit the formulas. Now this happens to have another formula for us. Check this out. Notice that if I have a set, let's call it B, let's put it inside of here. You recall B prime is the shaded region outside of B. So together they completely formed the whole set. So what we had then is B or B prime equals the whole sample space. So the probability, I don't know if I've put it or not, but the probability of the whole sample space is equal to 1. And now with that said, the probability of B or B prime equals the probability of B plus the probability of B prime minus the probability of B and B prime. Well, the thing is, B and B prime are completely disjoint. They have nothing in common because B prime specifically are those items that are not in B. So this piece right here is equal to 0. Well, we already did this one here. I'm going to put a 1 over here. Now, if I subtract P of B from both sides, I have another formula. I'll put it down here. P of B prime equals 1 minus P of B. So now I can start working the problems in this. Part A, they want us to have P of the probability of P of B prime, and I have, the last thing I wrote is the formula. That equals 1 minus the probability of B. And where is it? It's up here, 0.4. So we end up with 0.6. That takes care of part A. I might be able to fit part B in here. Let's try it. The probability of D and B. Well, let's see what formulas will be useful for us. I have this one. I have P of D slash B, so I'm going to use that version. So once you have that, you know this part is going to be P of B. So let me put that there, 0.5. And P of B is 0.4. So you end up with 0.2. What you're going to notice here is that they are going to, the way you work these problems is you need this one to solve like the next one, things like that. They kind of work as you go. P of B slash D, so now we're switching those. Well, let me write the formula for it. That equals P of B and D divided by the probability of D. Let me see if I have all this. We just did this one, 0.2. And D, the probability of D is 0.3. And so I'll write this to 6 decimal places. Next, the probability of D and B prime. This is important. Think about something. I want you to think about this. The probability of B slash D plus the probability of B prime slash D equals 1. Because here's what you have. This is the probability of something happening, and this is the probability of it not happening. So the probability that it did not happen, I mean, the probability of something happening or not happening is always 100%. That's why we get a 1 here. I am able then to go and subtract P of B slash D. And we just did that one. Finally, E, we want to find D, the probability of D slash B prime. So I'll write the formula for it and see if we've got all that I need. All right, let's see. Do I have D and B prime? That was D. Oh, I guess I never did. I guess I did not finish it. Let me go ahead and do it over here. That's going to equal the probability. I'm going to see what I'll put in there in a second, and I'll figure this second piece out in a second also. So what do I have here? I need do I have? Right. So I have B prime slash D. So I'll do that. B prime slash D because I know I have that. So this is 0.3333 times 0.3. So I think you'll find it's about 0.1 if you round. And when you finish this off, you'll get 1667. What we have here is a game of roulette. You may have seen this as roulette wheel. You throw the ball around the outer edge and it lands in any of one of 36 slots, red or black, but there's also 2 green slots that it can land in. These 2 up here, these 2 green ones. So what we have is we have 36 numbered slots, and these apparently don't count as numbers, but they are possibilities. So you have 2 possibilities that you could land in the green area. So there's a total of 38 outcomes here. So we have red and blue for 18 of 38, and we have 2 green. So we've got 18 red, 18 blue, and 2 green. Now, depending on the bet, the reason for that is on purpose. They don't want it to be even chance between it getting an even number, an odd number, or black number, or red. Notice the numbers are kind of weird too. They don't exactly go just evens and odds. They switch all of a sudden. You see this? They mix it up a little to make it a little more confusing for you. Anyways, let's look at some of the types of questions they have in this regard. All right, let's start on the first one. List the sample space, all 38 possible outcomes in roulette. So part A, I'm not going to write them all down, but you can do it like this. You can start writing G0, then G00, and then do, I guess we'll just do red 1, black 2, and go until I get to the very end, black 35 and red 36. So I'll put 3 dots in here, black 35 and red 36. Check to make sure that is true. Yes. All right, so now we start going through these. You bet on red. Well, there's 18 red out of 38 slots. So the probability of red is 18 out of 38. Same probability with evens. I'm sorry, with the black ones. You bet on the first dozen. So come up here, and when you're at the table, you get this. This is how the thing looks, how you can do your betting. The first dozen is over here, so you would lay your money in this spot here. And if any of these 12 numbers came up, you would win. So there's 12 possibilities there. Out of a total of 38. So that means the probability of the first dozen equals 12 out of 38. You can bet on the second dozen or the third dozen. You can bet odd, even, red, black. Notice that no choice that you make will have even a 50% chance of succeeding. You'll come close, but remember, since you're playing at their place, they're going to ultimately win all games in the long run. So while you get close to 50% odds some places here, it's always going to be less. You can double your money by doing these things. And any of these lines too, if you click on here, you might be you could probably do the first column for all I know. I don't know what the things are. You can go 1 to 18, then 19 to 36. All these are possible bets. If you pick a single number, you're going to win more money than if you pick odd, because picking odd is the risk is easier to pick odd and win than picking a single number and winning. D, you bet an even number. Well, we've discussed this. I think I'll just say even. we said there was 18 out of 38 of those. Now is red the complement? So let's see what we have here. It says, oh no, I'm sorry, is odd the complement of getting an even? So that means, does P of even plus P of odd, complement means these two add up to 1. So we know that if it's even, it's got to be 13 out of 38, and we know that if it's odd, it's got to be 18 out of 38. So let's try, if I add these together, since they have the same denominator, 18 plus 18 is 36. And that's not true. So this does not equal 1. So the answer to that question is no, they're not complements. The problem, it's made that way so that you stay less than 50% on any type of bet that you make. That's why they threw these two in here, these two green ones, to throw all that stuff off. Find mutually exclusive events. That's pretty easy. There's probably a million of them, but I'll pick something that's not straightforward. I'll say first dozen and a third dozen. If we go back up to the picture, they're quite mutually exclusive. This region is here, this region here. In fact, the first dozen is mutually exclusive from the second dozen, is mutually exclusive from the third dozen, mutually exclusive from these things. So there's all sorts of things that you could do. Pick odd numbers and even numbers, pick prime numbers and composite numbers, whatever. You can come up with all sorts of different possibilities. So find two mutually exclusive events. I was able to do that. And G, are the events even and first dozen independent? So remember, we want the probability of even and first dozen. Now they're independent if that's the same as the probability of an even times the probability of a first dozen. So the probability that something was even was 18 out of 38, and the probability of the first dozen was 12 out of 38. I'm going to go decimal on these, and so 18 divided by 38 equals, so I got that number. Now I'm going to go times 12 divided by 38. And what do we get for my answer? 0.1496. I'll go to 4 decimal places. 0.1496. On the other side, even and first dozen, let's take a look here. How many of the first dozen are even numbers? Well, that's going to be 6 of them. So we're talking about 6 out of 38 here. So the question is, this here is 6 out of 38 just by inspection. Well, let me have that on the calculator and see what happens. 6 divided by 38. Try that again. I did not type that correctly. Here I get 0.1579. So slash that. That means, are they independent? Not independent. Let's roll 2 dice. And let's count their sum. Now, when it comes to dice, if you roll 2 dice, the only thing you can get, the lowest number you can get is a 2, where both show a 1 on them, and the highest number you can get is a 12. So I'll put the sums along the first row here. So I'm going to have a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the only possible sums I can get when I toss 2 dice. Let's start with the number 2. I can get a 2 only by rolling snake eyes, as they say, a 1 and a 1. So I'm going to use an ordered pair to represent these two dice. They're two different dice. So this 3, I could have gotten a 3 by doing a 1 and a 2, or I could have switched the numbers like that. So in the first one here, this means the first die was 1 while the second die was 2. Here the first die was 2 while the second die was 1. Or if you wanted, you could look at it that way too. Rolling them at the same time is no different than rolling one and then rolling a second one and seeing what comes up. So for the 4s, I'll start with 1, 3, 2, 2, 3, 1. I'm trying to count these in a very specific way so that you can start doing your own thing shortly. Okay, I can get a 6 by getting, let's say I can do a 1 and a 5, 2, 4, 3, 3, 4, 2, 5, 1, 7, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. So hopefully you can see what I'm doing here. I'm just going 1, 2, 3, 4, 5, 6. I'm just counting down that way. Now with 8, I won't be able to do that because I can't do 1 and 7 because there's only 6 sides to a die. So I have to do 2 and 6. Likewise, the 9, I would start at 3 and 6. And actually 6 and 6 is going to be the only way that you can get a 12. But now let me write down all the ways that I can get an 8. I can do a 3 and a 5. I can do a 4 and a 4. I can do 5, 3. And 6, 2. Go over here. 3, 6, 4, 5. 5, 4. 6, 3. To get a 10, 4, 6, 5, 5, or 6, 4. An 11, there's only 2 ways to do that. And then a 12, you get a 6 and a 6. I have some questions and an example that I want to work. All right, so let's list this sample space. Well, the sample space is right up there. Here it is. There's 36 possibilities here. Check this out. The most probable thing that can happen is that you roll a 7, which is good because that wins. These numbers here, here, and here, if you add them all up, you'll see that there's a total of 36 numbers. So that should make sense to you because there's 6 possibilities for the first die and 6 possibilities for the second die. You do 6 times 6 equals 36. That's why there's 36 possibilities. So when you list the sample space, well, this here, this whole thing is the sample space. So I guess I can go S is equal to all that stuff. Let A be the event of a 3 or 4 rolled first, followed by an even number. So let's write that down, A. So the probability of A. Now what I'm going to do, let me take these pictures in here into consideration as I work the problem. So I'm going to grab this and copy it. The probability of A. All right, A was either a 3 or 4 is rolled first. So we'll go through this and take a look that either a 3 or 4 is rolled first. And then what else did they want? Followed by an even number. Okay. So notice that I can't even look at these because they don't start with a 3. The first one that starts with a 3 is here. Do I want it? I do not want it because it does not follow by an even number. Now I do want this guy because it's followed by an even number, but I don't want that one. I don't want that, but I want that. So it's got to be, the first number is either 3 and 4, and the second number is even. So here's a 3. Good, I'll take that one because it has a second number that's even. I won't take that one. 4 and 4, I will take that one, but I will not take that one. 4 and 5 I will not take, but I will take 3 and 6. Let's see, 4 and 6 right here, I will take that. And that's about all of them. How many do I have total? 1, 2, 3, 4, 5, 6. So the probability that that happens is 6 out of 36. Part C, let B be the event that the sum of the two rolls is at most 7. So the phrase at most 7 means less than or equal to 7. In other words, we want less than or equal to 7. So those that not only add up to less than 7, but we also want to grab those that add up to 7. So let me come back up here to my numbers. And this is going to be easy for us because that's going to be this column of numbers, and those to the left, those are the ones that have the sum of less than 7. So here, I'm just taking this amount of them. I wonder if I can erase that thing. No, I can't really get rid of it, but I can. I don't want that thing there. How many things do I have? So this is less than or equal to 7. Well, this column has 6. 6 plus 5, that's 11. Plus 4 is 15. Plus 3 is 18. 20. It looks like 21 total possibilities. So if I write the probability, this is B was what that was called. The probability of B is 21 over 36. Now, what you should probably do while you're going through this class is start to make yourself a piece of paper where you keep phrases of inequalities. Like this one right here, at most is important. We're going to be using things like that throughout the whole semester. So if these inequality words give you problems, you need to start collecting a list of them and what they mean. Part D, what is P of A slash B? Now, there's a couple of ways of doing it. You could say this is assuming that B has already happened. So the probability of A, assuming that B has already happened. Well, up here, this stuff up here was actually B. So I can actually treat this as if it's over the 21 units that are there and simply grab the ones that I want. So now I'm still looking for either starting with a 3 or 4 and then ending with an even number. So I would still not take this 3, 1, but I would take this 3, 2. Next, nothing else. The 4, 1 I do not want. 3, 3 I do not want, but I do want 4, 2. Is there any more? 3, 4 is one that I want. So this set has a total of 3 items. Are A and B mutually exclusive events? So E. So what I want to know, do I have A and B equal to the empty set? Well, let's see. There's B. And A were all those circled ones up there. So A had, so no, you can see that B was this triangle here, the left triangle starting from the 7 on to the left. Well, you can see that there's some circled items in there. That means there were items of A in there. So in fact, I'll write it out. Why not? It's going to be the circled items within those. So forget about those on the right. I want 3, 2, 4, 2, and 3, 4. Look at that. The only difference that you should know is the sample space associated with this only has 21 items. The sample space associated with this has 36 items, so be careful. Are A and B independent? So we've got a few ways of working that. One of them is the probability of A and B should equal the probability of A times the probability of B. This is, if they are independent, that would be true. So let me put a question mark if that's true. We did A and B. So the probability of A and B is 3 here out of 36. Now the probability of A, let me come back, where was that thing at? Was 6 out of 36. And the probability of B was 21 out of 36. You may try to do simplifying and see if it works out and everything like that. I don't know. I'm going to do a little simplifying the fractions. Feel free to do this with your calculators, but what I'm going to do here is the following. I'm going to cancel this 6 into that, and then I'm going to cancel a 3 into that one. So on the right, I get 7 over 72, which is not quite 3 over 36. If instead I use the calculator, which I'm assuming most people will do, I'll do 3 divided by 36. I get 0.08333, so 6 divided by 36, enter, times, let's see what that other thing is, 21 over 36. 21 divided by 36. 0.0972222. So you can see, since these things are not equal to each other, they are not independent. And I don't know what I did up here. Oh, this meant up here, this meant not mutually exclusive.